first speaker this afternoon is Ruxandra Moraru on commuting pairs of generalized structures, para-hyper-Hermitian geometry, and board geometry.
Thank you very much. And thank you very much for the invitation. It's a great honor to speak at the conference. And oh, it's not on? It is on. Okay, not. Yeah. Okay. So for me, when I think it is your work on the Higgs bundle that I first learned about. And it had a great impact on my thesis work, which was looking at moduli spaces of instantons on the Hawk surfaces. And I think something that has not been alluded to is that I do think that the Higgs geometry really had an impact on also looking at bundles over elliptic vibration. So a lot of the ideas, I think, really influenced that. So it had a big impact on my work. And because I'm interested in non-Kähler complex manifolds in general, it also came up again in generalized geometry. So later also came back to some other structures that you have pioneered. So today I want to give a talk that's maybe more of an advertisement on string structures that I recently started thinking about that I find interesting and that are related to generalized geometry. Okay, so I will start with just a basic review. Well, just make sure that I'm doing in the right direction. I think you did tell me, sorry. It's just, it's this. Oh, okay, so now it's starting. Mm-hmm. Okay, so my initial motivation for this work was understanding a little bit the relationship between Born geometry and generalized geometry. I'm going to define what Born geometry is soon. And the Born geometry came about because I co-supervised a student with someone at Ruxandra Institute who, through their work in what they call meta-string theory, gave the definition of what is known as Born geometry. So I need to introduce a few structures before I can give you the definition of Born geometry. So let me do a little bit of okay. So I'll be working over a smooth manifold, and then I will denote by Tm or T star in the tangent and cotangent bundles. And I'm interested in endomorphisms of the tangent bundle for now. And if you recall, what is a complex structure? It's simply an endomorphism of the tangent bundle that's first to minus the identity. And then we want to have some notion of integrability, which one way of stating it is simply that the plus and the minus eigenbundles are closed under the Lie bracket. I should know that for a complex structure, if either one of them is closed under the Lie bracket, automatically the other one is as well. Okay, and then you have the standard example of complex structure on R2N. And complex manifolds that emit complex structures always have to be even dimensional. Now there's another structure that one can put on a manifold, which is what is called a para-complex structure. This time it's an endomorphism of the tangent bundle that squares to the identity. And so it will have two possible eigenvalues, plus or minus 1. If you don't impose how many how many pluses you have and how many minuses you have what's known as a product structure. Here for para-complex, we're assuming that you have as many that the rank of the plus and minus eigenbundles is the same. Okay. But what can happen this time is that even if you have the plus eigenbundle that's close under the bracket, the minus eigenbundle will not. Okay, so if only one of them is closed, then you have this notion of half integrability that I'm told by physicists they're okay with. Then mathematically, it's natural to maybe ask that they're both closed under the Lie bracket. In which case, you have an integrable, almost para-complex structure. So I'm going to be assuming that we have integrability throughout the talk. Okay, and for some examples, of course, because I'm imposing that you have the same number of plus and minus eigenvalues, I mean, we're also again in a situation where we have an even dimensional manifold. And then here are some standard examples of para-complex structures on R2N or on Cn, where on Cn you can think of it as, one possible example is just conjugation, okay, of the complex variables. Okay, so these are the complex and para-complex structures. So for now, we just have an endomorphism of the tangent bundle, and then we may want to introduce a metric. So if we do this, well, if I start with the complex structure, and I take a Riemannian metric little g, then I can have two possible orthogonalities. Is there a pointer? Is the middle part a pointer? Or is it the top? Sorry. It's not working out. Okay, well. So, you have two possible orthogonalities. So if you have a standard if it's orthogonal, then you will have a Hermitian structure, which, you're all very familiar with. And then you can take the contraction of the metric with the complex structure, and you get this time a two form because of the orthogonality. And if that two form is closed, you have what is known as the Kähler structure. And another way of describing the Kählerness is that the complex structure is parallel with respect to the longitudinal connection. Now, if you impose the opposite orthogonality, then you obtain what is, I was looking through the literature. I guess some people call it anti-Hermitian, and this time, if you contract the metric with the complex structure, you no longer get a two form, you get again a symmetric tensor. And then you can ask that this complex structure is still parallel with respect to the longitudinal connection, in which case you'll get what is sometimes referred as an anti-Kähler structure. Okay, so that's what happens if you start with a complex structure and you pair it with the metric. And then you can do the same thing with the para-complex structure. And well, the first case I am imposing, so I have my J squares through the identity. Now to get a two form, I need the orthogonality for it to be sphere orthogonal. And so that's the first case of para-Hermitian. And then this time again, if I pair the metric with the para-complex structure, I get a two form. And if the two form is closed, I get the notion of a para-Kähler structure. I should point out that this is just linear algebra. In this case, the metric has to be signature and so we're no longer in the Riemannian case, well, it's sort of Riemannian case. And then you can impose the opposite orthogonality. And again, in the literature, there is various terminology. I will call it chiral for now, motivated by the physics. And in that case, as in the anti-Hermitian case, the contraction of the metric with the para-complex structure is now again a symmetric tensor. And you can ask for it to be a Kähler type if you impose that the para-complex structure is parallel with respect to the longitudinal connection. I should point out that the para-Kähler examples are interesting because you do get a very natural, so in that case, the form omega is closer to symplectic structure, and then the plus and minus eigen bundles are Lagrangian with respect to that omega, so you get a bi-Lagrangian structure on your manifold. So they are interesting geometrically from that point of view. Okay, so that's the classical setting. And I'd like to, so this is more where I came, the direction I came from. And I discovered, I was familiar, of course, with the Hermitian case, but with the other cases, I wasn't so familiar with. And well, now you can consider more than one complex structure, or maybe more than one para-complex structure. So if you do that, well, one case that's been studied a lot is if you have a triple of complex structures, and then two of them and the anti-commute, so you get what's known as a hypercomplex structure, and then you can pair it with a metric, in such a way that each pair of each complex structure paired with a metric gives you a Hermitian structure. And then, of course, if the corresponding fundamental forms are closed, you get a hyper-Kähler structure. And then I just want to point out that one way to interpret para-hyper-Hermitian structure is as a bi-Hermitian structure, so two complex structures and the metric which is Hermitian with respect to both, but the complex structure is anti-Hermitian. So that's one way of thinking of a hyper-Hermitian structure. And the reason I want to think of it that way is that, as Marco told us, this is how this is related to generalized plane geometry. Okay, so hyper-complex geometry, hyper-Hermitian geometry is, is included in generalized scalar geometry. Okay, and then you can do the same thing now with the para-complex structure. This time, what one can look at is a triple where I is complex and J and K are para-complex, and they all anti-commute, and also I is equal to J and K. So I forgot to, I think it was written for the hypercomplex space. Okay, so this is what we can ask. And then, of course, you can pair it with the metric. Now, because of the fact that I have two para-complex structures, my metric is now going to be pseudo-Riemannian, no longer positive definite. And then, well, we can ask that the metric that we choose is going to be Hermitian with respect to the complex and para-Hermitian with respect to the two para-complex structures. And then we obtain what's known as a para-hyper-Hermitian structure. So, and so we have, because of the orthogonalities, if we pair the metric with each of these structures, we obtained a triple of two forms. And if those two forms are closed, oh, I forgot to my two comments. But if maybe I'll already here, I'll come back to it. If those two forms are closed, we get what is known as the para-hyper-Kähler structure, or also hypersymplectic. I guess I think maybe you introduced them first, or we were.
I chose the word
hypersymplectic, yeah. So a lot of people have done work on this, and even here. So hope I'm not forgetting too many names, but there has been work of Ivanov and also Fino and also Danter Swan, one of Andrew's students, Rosen and Grantjarov has also done quite a bit of work on this. And one thing that I should say is that here these structures only it imposes that the manifold is 4n-dimensional, okay? And also there are some topological constraints a little bit on the underlying manifold for these structures to exist. Okay, so, and maybe I should say that, again, to bring it back to this generalized geometry setting, one can think of these para-hyper-Hermitian structures as being a pair of para-complex structures, let's say J and K, and with the metric G, which is where JG and KG are para-Hermitian, sorry. And then your para-complex structures and okay, so and this is why it will be natural to think of it in the context of generalized geometry. So I thought I would give two simple examples. These I think are not as familiar as the hypercomplex. So for example, if you're on R4, this J and K that I wrote down will square to the identity. And then if you take the metric little g that I wrote down, then and J and K anti-commute. So so it'll give you a para-hypercomplex structure, and paired with the little g that I wrote down, it will give you, if you're over R4, it will give you a para-hyper-Kähler structure on R4. And if you divide the little g by the norm squared in R4, it'll actually descend to a para-hyper-Hermitian structure on the Hopf circuit called S3 cross epsilon. And here it's not hard to check that it will not be para-hyper-Kähler. So the corresponding fundamental forms will not be closed. Okay, so that's an example. And I guess because we have been revisiting some of your papers, this is a very hard paper to find, and I was very lucky that I obtained a copy in June when I was in Oxford. So this first appeared in this paper that by Nigel here, hypersymplectic quotients. And the example of how these structures appeared is in harmonic maps. So these are related to the Higgs bundle, but the equations have a sign difference where on the moduli space of the solutions to the harmonic maps, the natural triple that one obtains is para-hyper-Hermitian and not hyper-K. I mean, the quadruple, I should say. Okay. So this is, and so this is something that, I mean, I almost also was going to put a picture of Andrew, then to give me a very welcome copy of your lecture note that he gave at CFM, I think in the mid-80s, were also being appear. But maybe not, I'm not sure if you already had the hypersymplectic structure there, but you certainly had, no, I think maybe, certainly the harmonic maps are kind of at the end of the lecture notes. So. Anyway, all right. So these are some of the. This is what has been known for some time, and now I can give you the definition of a Born structure. So for a Born structure, what you do is that you again start with a para-hypercomplex triple IJK. So JK are paracomplex, I is complex, and it's the product of JK and anti-commute. And this time, I'm going to pair it with a metric. Again, I don't have any choice. It has to be pseudo-Riemannian if it's going to have some natural compatibility with the paracomplex structures. But the way I'm putting the orthogonalities is that now the pair IJ, I being the complex structure, is anti-Hermitian. And then the KG is para-Hermitian. And then the JG is going to be chiral. So it's a little bit of a mixture. And these structures were introduced by Friedel Ley-Minnick as the proper background for what they call meta-string theory. So I unfortunately can't explain to you, can't tell you much about the physics, but that this was the natural background that they were using. And as I mentioned, I co-supervised David Svoboda with Laurent and also Shengda Hu, who's part of this project. And Shengda and I were kind of focusing more on the mathematical side of things, and then David and with Laurent and developed, and also Felix Rudolph really developed the physical properties of these structures. And what I should mention is that unlike the para-hyper-Hermitian case, these Born metrics exist. I mean, first of all, there's no, if you just start with the para-hypercomplex structure, it can exist on any two n-dimensional manifold. And then pairing it with a metric does not impose any extra condition on the dimension. And if you start with any para-hyper complex structure on a manifold, you can always find a metric that pairs up with it to give you a Born structure. So that's always possible. So they always exist. And then we looked at some examples, and we're able to come up with examples on a lot of compact floor manifolds and on total spaces of tangent bundles. So this is just the beginning. I think they're kind of interesting, but I have to say that we're kind of just basically looking at a lot of the work that was existing in para-hyper-Hermitian geometry and just tweaking a little bit the examples so far. So,
Sorry, is there
yes.
a Holonomic reduction here for the metric?
I don't know. No, I mean,
Something is a prevent.
no, not necessarily. Yes, well, sure. For now, it's almost, but in the generalized situation, yes. So to make it work with the generalized complex, things have to be parallel. But I think in general, it's not part of the definition. You could have something that is not. Yeah. So in particular, for example, like on the hot surface, they're not parallel. So in some of the examples, they're not always parallel. Okay, so these are the structures. This was the motivation, and to bring it back to see how it fits into the generalized geometry. Again, one can really think of the hypercomplex structure as being given by these two paracomplex structures, the J and the K, that anti-commute. And now, I gave you this original definition of Born geometry, but if I just take one of the corresponding metrics that we obtained, because you see, IG is anti-Hermitian, so the contraction of little g with I is a metric again, and even the chiral, the pair, gives you another metric. And if I take the second one, the one that I obtained by contracting little d with j, which is again a metric, I now get IJK, and this new metric will give me, it's another way of thinking of my Born structure, but now will fit in well with the generalized geometry point of view. And maybe one more thing that I can say is that what is interesting is that if you start with a para-hypercomplex structure and you try to pair it with a metric, you actually essentially just have two possibilities. You either are in a para-hyper-Hermitian world, or you're in this Born geometry world where you have like three metrics that you can play with, right? So it's almost like dividing the two possible, the structures into two possible camps. Okay, so not a lot is known about this Born side of things. I think it's interesting, but so maybe this first part is maybe just kind of an advertisement for this geometry, this newer kind of geometry. Okay, so now I want to move on to the generalized geometry, but before I do so, there are more questions, or okay, so there are none. Then let me do a little recap. I know that we've seen already a couple of talks on generalized geometry. So I'd like to see a little bit how para-hyper-Hermitian geometry and word geometry, how they are coming up in this generalized geometry setting. Okay, so let me now say that I'm going to fix the manifold. Okay, so I have N, which is a real manifold that's unidimensional. And I'm going to fix a real closed real 3 form on the manifold, capital H. And this time in generalized geometry, we're not just considering the tangent bundle, but it's the direct sum of the tangent bundle, the cotangent bundle. And we have two natural brackets that we're considering on T plus T star. So there's a symmetric pairing that you have here, and also I'll be using the Dorfman bracket. Okay. And using these two, then what you can do is, well, you can now consider endomorphisms of T plus T star. Oops, okay. And I'm going to be much more general about it. I mean, so far we were seeing our endomorphism corresponding to some generalized complex structure. Here, I'm just going to consider a pair of endomorphisms of T plus T star. And they will either square to plus the identity or minus the identity. And so for a generalized complex structure, you want it to be orthogonal with respect to the symmetric pairing. Here, I'm going to allow it to sometimes be skew orthogonal. Okay, so this is how I'm going to the conditions that I have on my two endomorphisms, and I want them to commute. Yeah. And then you have 4 possible cases for these signs, alpha, beta, or just plus or minus. So the first is that J1 and J2 squared to minus the identity, and they are both orthogonal with respect to the symmetric bracket, which is what generalized geometry is. No, generalized scalar geometry is. And then if I take the opposite convention, that the J's squared to the identity, but now they are skew orthogonal with respect to the symmetric bracket, this is what we call generalized para-hyper geometry. And then if J squares the identity and they're both orthogonal, we were calling it generalized chiral geometry. And I guess the last possibility where we have the both signs are minus is what we're calling generalized anti-Kähler geometry. But you analyze them all in a similar fashion. I'm going to just focus on the para-Kähler and the chiral geometry, although I'll do a very quick summary of what is known about the generalized Kähler that we then kind of developed for the other cases. And okay, so in all these cases, so J1 and J2 are endomorphism of T plus T star that commute. So if I take their product, I'll call it G, capital G, then the G will square to the identity. And then you can consider, because it's for the identity, the only two eigenvalues are plus or minus 1, and you can consider the plus and minus eigenbundles. And those are subbundles of T plus T star, but you can take the projection to the tangent bundle to T. I'm calling them plus or minus. So these are the natural projections. And then Well, in generalized geometry, you're assuming that the capital G is positive definite, so you know that C plus and C minus will be isomorphic to T. So the projection phi plus and minus will be isomorphism. Here in the setting that we have, because we're going to allow things to not necessarily be positive definite, but also, indefinite, we're going to just assume that these projections are isomorphisms, and it's enough to make all the kind of constructions follow through. And this is what we'll think of as being a generalized metric. And then, of course, if you're generalized Kähler setting, then your G is positive definite. Okay, so this is the setup. Okay, and then using these projections, so we're assuming that the projections from the positive and negative eigenbundles are isomorphic to T, to the tangent bundle, and using those, we can recover some classical structures. First of all, a Riemannian or pseudo-Riemannian metric, just on the manifold, just on the tangent bundle of the manifold, and also two endomorphisms of the tangent bundle that will square to or plus or minus the identity depending on what J1 and J2 square to. So in the sense that if you're generalized complex structures, then the two classical structures J plus minus on the tangent bundle will be themselves complex, but if this first two minus the identity, they will become para-complex. Okay. So, so far everything works as in the generalized Kähler setting. And then I just want to mention that you also have this notion of a generalized Bismuth connection, which can be used to characterize integrability of the generalized structures. And the reason I'm mentioning it is because even though integrability of a generalized complex structure can be completely described using the Dorfman bracket, in the case of what we were calling chiral geometry and anti-generalized Kähler geometry, it's impossible. You don't have a well-defined notion of Nain-House tensor, generalized Nain-House tensor. So we define them in terms of Nain connection, integrability. That's how we characterized integrability. Okay, so but these are a little bit the objects that are coming up. Okay, so what I'm going to do is just do a short survey, a recap of generalized Kähler, and you will see what is known in the generalized Kähler setting, how it adapts to. So as I said, I'm focusing on the generalized para-Kähler and the chiral setting. Okay. So, but let me start with generalized Kähler. So in that situation, we are dealing with generalized complex structures, which are endomorphisms of the T plus T star that's square to minus the identity, and are also orthogonal with respect to the symmetric bracket. And there, well, we can consider the plus and minus eigenbundles, and the integrability of these almost generalized complex structures is determined by whether or not these plus and minus eigenbundles are closed under the Dorfman bracket. But as I mentioned, there is a well-defined generalized Nain-House tensor, so it's also the same thing as requiring that the generalized Nain-House tensor vanishes. Okay, and then they were of course first introduced by Nigel, and then Marco and many other students of both Nigel and Marco's NGO have studied this case. Okay. And what I want to just mention is that this integrability, which is the second condition that I wrote down, one can describe it in terms of a generalized Nain-House tensor, because in that case, the plus and minus eigenbundles are isotropic with respect to the symmetric bracket. So it means that this generalized Nain-House tensor is actually a tensor, and so you can define the integrability in terms of that. Okay. And then, of course, you have the general, the standard examples that come from, if you start with the symplectic manifold, you have a natural induced generalized complex structure. Same thing with the complex manifold. And so that's why, you can think of these structures as interpolating between complex and symplectic geometry. But then you also, when you see that part of the story is holomorphic puzzle structures, and then, if you start with the holomorphic puzzle structure and you take the imaginary part, you can define in a natural induced, you have a natural induced generalized complex structure on the manifold. So these are the standard examples. And for generalized scalar, what you do is that you have a pair of generalized complex structures that commute. And also their product is positive definite. So it's a positive definite metric on T plus T star. And, as Marco mentioned, you can, of course, if you start with a Kähler manifold where you have both a complex and a symplectic structure, it gives you a natural pair of generalized complex structures that commute and actually give you a generalized Kähler structure. And by the construction that I outlined before, if you start with any pair of any generalized complex pair, generalized Kähler pair, this will give rise to a bi-Hermitian structure. So two complex structure, I plus or minus Riemannian metric little g, such that the pairs I plus little g and I minus little g are Hermitian. But also there's an extra condition that the fundamental forms are not necessarily D-closed, but they're DC, they're not even necessarily DC closed, but they, if you take the twisted differentials of the fundamental forms, they differ by sign. Okay, and they're actually equal to the initial, the capital H here, it's not a coincidence, is the initial closed three form that that one uses to define the Dorfman bracket. Okay. So, I mean, and these structures are known as pluriclose, and Jeff will tell us more about this right after me. Okay, so this is what you have. And of course, if the bi-Hermitian structure that you obtain, if it anti-commutes, then of course you have a hyper-Hermitian, you're working with a hyper-Hermitian structure. Okay, and then as Marco mentioned, you can reverse the process. So if you start with any bi-Hermitian manifold, whose metric little g is actually pluriclose with respect to the two complex structures I plus and I minus, then this gives you a generalized Kähler structure, and Marco proved that, I mean, those early thesis that you have one-to-one correspondence between these generalized Kähler structures and also these bi-Hermitian structures whose metric is pluriclose. Okay, so that's why there are equivalent ways of thinking of generalized Kähler structures. But I want to mention two more facts about this. So another one, oh, okay, I'm sorry, I forgot. I wanted to give you some examples that, for example, of course, hyperkähler manifolds give you examples of bi-Hermitian structures, of generalized Kähler structures. And then, as Marco mentioned to us on yesterday, that Hopf surfaces admit generalized Kähler structures. Even though Hopf surfaces cannot admit Kähler structures, they do have generalized Kähler structures. So one way to see this is to think of the Hopf surface as being constructed using the quaternions. So you take the quaternions, you remove the zero, and then you take the quotient under this natural Z action that you obtain by fixing a real number between 0 and 1 and saying that two quaternion Z the quaternion Z and Z times Q are equivalent. So the quotient will give you a compact surface that's a four manifold that's diffeomorphic to S3 plus S1. But because you're taking the quotient by the quaternions, multiplication by IJK give you three complex structures that descend to the quotient. And actually here, oh, I'm sorry, I was going a little too quickly. We just want a bi-Hermitian structure. So here we take multiplication by I and from the left and from the right, and these will give us the two complex structures, I plus and I minus, that give us our natural generalized Kähler structure. With respect to the metric little g that I wrote down, which is essentially just the Taylor metric on C2, but quotiented by the norm squared so that it can descend to the quotient. Okay, so this is example of a generalized Taylor structure on a hot surface. Okay, so and then as I mentioned, I wanted to mention two more things about generalized Taylor structure. So the Marco and also Vesti spoke about the fact that you do have this natural Poisson structure that you can obtain using starting from a generalized Taylor structure that here I'm describing in terms of the corresponding bi-Hermitian structure. And this Poisson bivector is going to be holomorphic with respect to both complex structures I plus and I minus. So that's the relationship, another relationship with Poisson geometry. And I also wanted to mention this characterization of integrability that's due to Marco, which is in terms of this generalized Bismuth connection, that a generalized Taylor structure is going to be integrable if and only if the two generalized almost complex structures, J1 and J2, are parallel with respect to the Bismuth connection. Here, capital B is the generalized Bismuth connection. But also you want that the generalized torsion is of type 2, 1, 1, 2 with respect to both of those generalized complex structures. So that's another way of characterizing integrability of J1 and J2. That's going to be useful. Okay, so that's generalized Taylor. All right, so if there are no questions, then let me now go to the para setting. Okay, so you can do the same thing, but this time you take a pair of endomorphisms of the T plus T star that's square to the identity and have this pure orthogonality with respect to symmetric pairing. This time because the J's square to, oh no, sorry, I don't have a pair yet. I mean, here I'm just looking at a generalized para-complex structure. So it's square to the identity and it's pure orthogonal with respect to the symmetric bracket. And because it's square to the identity, the eigenvalues are plus or minus 1, and you can ask for those to be closed under the Dorfman bracket again. And these were first introduced by Aisha Wade in 2004. I mean, I think she was interested in integrating things between pre-symplectic structures, and also she's interested in compact geometry, where there was the natural, they came up in a natural way in her work. And as before, I want to point out that it'll work exactly as the generalized Taylor structure, and in particular also because if you take both the plus and the minus eigenbundles, they are isotropic with respect to the symmetric pairing, and so you have a well-defined notion of generalized Nienhaus tensor, and so integrability, the second condition, can be just it's equivalent to saying that the Nienhaus tensor vanishes. Okay, and as for standard examples of these generalized para-complex structures, well, you can again start with the symplectic manifold, and you have a natural induced generalized para-complex structure. I mean, the difference with the generalized complex is just the sign. In the generalized complex, you have a minus in front of one of the omegas. You can also generate in a natural way a generalized para-complex structure, start with the para-complex structure on the manifold. And then also you can start with the real Poisson bivector and a para-complex structure and generate you have a natural induced para-complex structure. Okay, so and now, well, once you you can consider a pair of these. Oops, as before. I mean, as in generalized context, where I take a pair of generalized para-Taylor structures that commute, and I consider the product capital G of the two. And now we're asking that it's a non-degenerate metric again because we're in the para setting. These will have to be actually. They will not be positive definite, but we can still ask for the capital G to be non-degenerate. And not surprisingly, if you start with a para-Kähler manifold, so then you have your para-complex structure J and your metric little g, such that the fundamental form is closed, so it's a symplectic structure, then you have the induced generalized structures that give you a generalized para-Kähler pair. And as for generalized Kähler, if you start with a generalized para-Kähler pair, J1, J2, then you obtain these structures, these classical structures on the tangent bundle, so the J plus and minus and the pseudo-Riemannian metric little g, where you're actually getting a para-by-Hermitian structure. But it's not just that, it's a little bit like the pluriclose condition, but it's the para version. So the fundamental forms are such that here I'm not writing down the definition, the dp plus or minus. I mean, you have a plus and minus eigenbundle, so you can have a decomposition as in the complex case of your forms on the manifold. You have a vibrating, and then and then the dp plus or minus is defined as in the complex case by twisting the differential, the d by the parent complex structure. So I've written down the definition. The definitions are very similar. So this is, but if you start with a pair, a generalized para-Kähler pair, you obtain a para-by-Hermitian structure where the fundamental forms have that property that is very similar to what happens in generalized Kähler geometry. Okay. And as before, you can reverse the process. So if you start with a para-by-Hermitian structure such that the fundamental forms have that, we haven't named it, but it's like a pluriclose condition, then you can reconstruct your generalized para-Kähler structure, a pair J1 and J2. And well, you can prove that there's a one-to-one correspondence between these things. And oh, sorry. Okay. And then I'm sorry, I'm going a bit too quickly, but and then you have your standard examples. So when at the beginning of the talk, I was motivating things by considering these para-hyper-Kähler, or if you want hypersymplectic manifolds. So those give you examples of generalized para-Kähler structures. And then also the para-hyper-Hermitian structure that I gave you on the Hopf surface also gives you an example of a generalized para-Kähler structure. Okay, so you do have a lot of these manifolds. I mean, so there are many examples. That's I guess what I'm trying to say. There exists a lot of examples of these structures. Okay. And I wanted to say that then you can redo everything that you have in the generalized setting, that this time, if you start with a generalized para-Kähler structure, you obtain a natural Poisson bivector, which will be para-homomorphic with respect to the two para-complex structure J plus and J minus. And also, you can describe the integrability in terms of the bismuth connection. Okay, so I mean, it's very easy to adapt the work that's in the generalized Kähler setting to this case. Okay, where things were a little bit different is in the chiral setting. Okay, so I want to, I'll just end by telling you a little bit about what happens in that setting, which is where Born geometry lives. So this is the setting that we're initially interested in. It's just that while working on it, we realized that you can, it works out, and you can work it out for all the other cases. Okay. So here, what we want is what we called a generalized product structure. So it's an endomorphism of T plus T star that squares through the identity, and it is also orthogonal with respect to the symmetric brackets. And this time, though, the plus and minus eigenbundles of J are no longer isotropic with respect to the symmetric bracket. So there's not a well-defined notion of an in-house tensor. And so we had to just find a way of defining integrability for those structures, because so far, you know, if you just have the, all I'm imposing is that J squares to the identity, and also it's orthogonal with respect to the symmetric bracket. So we didn't yet have a good notion of integrability. But, you know, if you think of examples, the generalized metrics are examples of product, what we call these generalized product structures. And then, you know, you can also cook up many examples. If you start with the complex, para-complex manifold, you have a natural induced product structure, the one that I'm bringing down there. And also, if you start with the pseudo-Riemannian manifold, you can use a pseudo-Riemannian metric to define in a natural way one of these generalized product structures. Or I should call them for now almost, right? I don't have yet a good notion of integrability. And so what we defined as an and if we just have one structure by itself, we still didn't have a good notion of integrability. But when we were putting it in a pair, we're taking a pair of these product structures, and we're calling it an almost generalized chiral structure, just in reference to the physics. That, you know, I'm not saying it's the best word for it. So we're taking a pair of two product structures that commute, and such that the product, capital G, is a generalized metric. In the sense that the restriction to the plus and minus eigenbundles was an isomorphism onto the tangent bundle. That was our condition. And so, you know, you have examples of these. If you start with an almost chiral manifold, so J is an almost para-complex structure, and G is a pseudo-Riemannian metric such that well, no, it doesn't have to be necessarily just yeah, it could be positive definite. We're not putting in a condition, but such that J is symmetric with respect to orthogonal with respect to G. Then, you know, you have these two induced product structure, and the pair will become one of these almost generalized chiral structures. And you can reverse the process as before, right? If you start with such a pair, you can obtain two endomorphisms of the tangent bundle J plus or minus, which happen to be para-complex, and, you know, so there's a one-to-one correspondence as before between these almost generalized chiral structures and these, I guess, for what one could call bichiral structures on the manifold, on the tangent bundle. But for the integrability, because the plus and minus eigenbundles of the generalized structures are not isotropic with respect to the symmetric product, we decided to give a definition using the generalized bin with conjunction for the integrability. So this was our definition. So it's almost like what you have in the generalized scalar case and the para case, where you want those two generalized structures, the J1 and J2, to be parallel with respect to the generalized Bismuth connection. But then we wanted the generalized torsion to be of type 3003. And it may seem a little surprising, but this was forced by wanting to have a similar result as in the other two cases where, oh, sorry. Okay, almost there. Where the pair J1, J2 was integrable if and only if. So if you remember at the beginning of the talk, when we had a chiral structure, one way to describe scalarness, if you want, of that was that the structures were parallel with respect to longitudinal. Okay, so this was the natural result to obtain in this situation, that the pair J1 J2 was integrable if and only if the corresponding para-complex structures were parallel with respect to the longitudinal connection of the little g. And it's a little bit technical, but the reason why this was natural was if you in this chiral setting, there's a fundamental tensor that's natural that comes up. And if you even look at the classical setting, it is really the 3003 components that show up in the natural link. And they need to vanish in order to ensure integrability even in the classical structures. So this was the definition we gave, and we obtained the result that we wrote down, even for these generalized chiral structures. And Born structures are an example of these integrable generalized chiral structures. But not all Born structures will have that because they have to be of hypercator type, meaning that the paracomplex structures have to be parallel with effectively to that. It's a bit more restricted. They're special, but in any case, this is what we obtained. Okay, so that's, I guess. I mean, I think that this is pretty much what I want to say. I mean, it was natural for us to think of this generalized geometry because in the physics side of it, you have a lot of these double geometries appearing. And so, you had somehow this generalized geometry that was appearing in the physics. So it was intriguing to look at it from that point of view. But I do find the Born structures and also these para-hypersymplectic structures interesting, even as related to my previous work that, for example, cadaver surfaces that I'm very interested in emit para-hyper structures. And I wonder if some of the work that Nigel did on bi-dimensional structures on instant moduli spaces, all these things can be kind of worked out a little bit in the Paris setting. I know that Gil has, I've spoken to him a little bit about it. I don't know to what extent that can get through, but I think that there are some interesting directions that one can go in that is related to this story. So, but I will stop here now. So, thank you.